Welcome to the module Waves. Today we'll discuss standing waves. Standing waves are waves where all the points on the wave are oscillating in the same harmonic fashion, but with a different amplitude. So let's go back a little bit to the wave equation. We have seen that the solution to the wave equation is a function u x of t that is a traveling wave, a sine kx plus minus vt plus a phase phi. Now this is a wave that can travel in the positive x direction or in the negative x direction. Both are solutions to the wave equation. Alright, now let's consider a string that we fix together on two fixed points at the sides, expanding a distance L, and we retract that string a little bit. Now what happens? Well, of course, the string starts to oscillate. But from the viewpoint of the string, you could just as well say that from this position, two traveling waves start to propagate. One to the right-hand side and one to the left-hand side. So if we assume that they have a kind of this cosine-shaped waveform, then we can look at what the waves looked at different times. So initially, this wave will start to propagate in this positive direction with the shape that is given here in red. This is the first time that we see the wave, and then a quarter of a wavelength later, we see, of course, that the wave has propagated and that it reflects onto this fixed boundary. Thereby, its amplitude is inversed and it propagates further. But there's also a new part of the wave that comes into play, and this is the top-hand side, where this is a positive amplitude. Also, on the negative side, negative propagation side, we see the same phenomena occur. And if we add up all amplitudes together, we see that we have a wave with an amplitude of actually 0. After a later time, the wave again starts to propagate. So the bottom part again propagates to the left, the top part propagates to the right and flips around. And the same thing happens for the left-hand side. So after again a quarter of a wavelength, we see that the entire waveform shape has now flipped its sign and is now at the bottom part. We can also describe this mathematically. So the total deviation, displacement, is equal to two traveling waves, one in the positive direction and one in the negative direction. And if we apply some trigonometry, we can see that this is a function 2a sine kx cosine omega t. That means that the wave has a certain fixed pattern in space, sine kx, that determines essentially the amplitude of an harmonic oscillation in time, cosine omega t. Alright, so now let's look at a few examples. So first we look at the fundamental mode. So we can have a propagating wave with different wavelengths. And the wavelength can be have a continuous dimension, but only a few of them are supported by this standing wave pattern between these two fixed points. So the wavelength can be 2L over n, with n equal to 1, 2, 3, etc. So the first harmonic is given by n equals to 1, and the frequency is equal to f is equal to the speed of the propagating wave divided by the wavelength, which is then 2L. So you see here how the wave oscillates, and that certain points have no movement, but other points have a large amplitude. Then the second harmonic, that is a wave that has an entire wavelength in between this length L suspended between the fixed points. Again, in this case, the frequency is given by V over the wavelength, which in this case is L, and we get a frequency that is twice as high as for the first harmonic. This is also what you see in this picture. Note again now that there are 3 points that don't oscillate, and that there are 2 points that oscillate with the maximum amplitude. The third harmonic is even a higher order harmonic, where now 1.5 wavelengths fit into this length 2L. So again, we can calculate the frequency, and this is again 1.5 times larger than this frequency, that of the second harmonic. Okay, let's look a little bit more into these points where there's oscillations and no oscillations. This is what we call nodes. Are the points with zero amplitude. And antinodes. These are the points with maximum amplitude. Now the nodes are of course given by where this spatial dependence of the wave, sine kx, is equal to 0. There the oscillation amplitude is 0. And we find that when kx is equal to 0, pi, 2 pi, etc. So for our standing wave we can find that at 0, lambda over 2, lambda, 3 lambda over 2, etc. Of course depending on what lambda is. The antinodes are the points with the maximum amplitude. That is where sine kx is equal to 1. These occur, of course, when the argument of the sine, which is kx, is equal to pi over 2, 3 pi over 2, 5 pi over 2, etc. And so these occur at quarter wavelength, 3/4 wavelengths, and 5/4 wavelengths, etc. Okay, let's look at an example of the second harmonic. There we can see that there are nodes. These are the points with zero amplitude. And they occur at x is equal to 0, lambda over 2, lambda, 3 lambda over 2, etc. But now with lambda equal to L. So that means that 0, which we can see indicated here in red, equal to L over 2, which is right in the center, and at equal to lambda is L, which is on the right-hand side. Also, there are antinodes. These are the points with maximum amplitude, and I've indicated them in green. You can see them here at lambda over 4 and 3 lambda over 4, which are equal to L over 4 and 3/4 L. There, the amplitude of the standing wave is maximum. All right, so far for all the theory of the standing wave. But now let's look at a few applications. Well, there are many, but let's look at the most interesting one. These are music instruments. And then we consider first what we call pipes. There are many different kinds of pipes, so like flutes and trombones. We'll look at them later. But what happens in a pipe? In a pipe we have a column of air that we can let resonate. And in that case there are longitudinal waves that travel in the pipe and that create areas of low pressure and high pressure. In the areas of low pressure, the molecules are moving, displaced from their center position. And this is the displacement that we usually describe with this U. That also means that acoustic waves in pipes are a longitudinal wave, pressure waves. Again, we can calculate the temporal frequencies by using the relation omega is kV. But now in this case, we have to look what V is. So V is the speed of sound in this pipe, or in this air column that is in this pipe. And this is given by the square root of gamma kBT over m, where gamma is the heat capacity ratio, kB is Boltzmann constant, T is the temperature, and m is the mass of the molecules that are in the pipe. Again, we can calculate the frequency based on this formula. However, the wavelengths that we used for calculating this frequency are set by the boundary conditions of the pipe. They can also be open or they can be closed. Let's look at two examples. Let's first look at the flute, or in this case the recorder. This is an instrument that has an air column stretching from the top to the bottom and that is open on both sides. That means it supports a fundamental mode that has a wavelength that is equal to 2L, just as we've seen it for the strings. But you can also change now the resonance frequency of the mode in the pipe. You can do this in a few ways. I will show you. Okay, so here you see a flute. I can whistle on the flute or blow in the flute from this side, and there are holes in the flute on this side. So there are a few ways that I can change the pitch of the flute. The first way is to change the velocity with which I send sound waves into the flute. You can hear it in the following way. You see that the pitch goes up since the velocity goes up. The other way is to change the length of the flute. By closing more holes, I can essentially make the flute longer because where the hole is, that's where the first open location is, and that's where an antinode will occur. So in this case, you can hear that the pitch goes down because essentially the flute becomes longer. As a second example, there's the trombone. This is an instrument that has an open end at one side. This is just similar to what we have in the flute. But on the other hand, there's a mouthpiece where you cover it with your mouth. So that's essentially where it is closed. And that's why the whole pitch of the trombone is arranged in a different way. But you can change the pitch by blowing it differently, but also by changing the length, and thereby just changing the fundamental frequency of the trombone itself. Okay, now let's have a look at music instruments with strings. In this case, our displacement that we calculated, U, is essentially the displacement of the string with respect to its equilibrium position. So the wave along a string is a transverse wave, where the oscillation is perpendicular to its propagation direction. Again, we can calculate the temporal frequency of our standing wave using the relation omega is kV. But in this case, we need to calculate the speed of the propagating wave in the string. And this is dependent on the square root of the force on the string, the tension, divided by mu, which is the mass per unit length. If we combine these two, we find that the frequency of the standing wave is equal to 1 over lambda times square root Fs over mu. Of course, again, in this case, the wavelength that is supported by the string is given by the boundary conditions. However, in all string instruments, the boundary conditions are that the displacement is 0 at both sides, because that is where the string is suspended between. So in this case, the wavelengths are 2L divided by n, with n an integer equal to 1, 2, or 3. So finally, we end up with this relation F is equal to n divided by 2L square root Fs divided by mu. You may have seen this equation at the introduction of this course. Okay, now let's have a look at a few instruments. The first one, that's the violin. In the violin, we can change the length of the string by putting our finger at a different location on the fingerboard. In this case, we can change the pitch of this fundamental mode continuously. However, the violin also gets its nice sound because it resonates also all the other higher harmonic modes that are given by the length of the string that oscillates. Now, contrary to that, we can also have a guitar. Here's a nice example of it. And in the guitar, of course, we can also change the tension by twisting this and creating a higher pitched signal. And also what you can see is that there are strings, some of them have a lower mass per unit length, such as this one, compared to the ones that give the lower pitch sound, compared to this one. Also, we can change the length of the string, but not continuously, but only at the locations where we can put our finger close to a fret. So for example, if we halve the length of the string, we get twice as high frequency. This is called an octave. All right, now you have seen how the music instruments work and how the standing waves play a big role in that. Thank you.